Tonight, we're going to talk about something that happened more than 4 billion miles from Earth. Something that a single small spacecraft, no bigger than a grand piano, sent back to us in fragments of radio signal that took more than 6 hours to arrive. In January of 2019, New Horizons, the same probe that had given us our first close look at Pluto 3.5 years earlier, flew past an object so distant, so cold, so untouched that no human eye had ever seen it before. The object was a frozen world in the outer reaches of the Kuiper Belt, billions of miles beyond Neptune, in a region of the solar system that scientists had spent decades imagining, but had never been able to visit. And what New Horizons saw there did not match what anyone had expected. The official name for the object is 486958 Arrokoth. It looks, in the photographs the spacecraft sent back, like two reddish snowballs gently pressed together, frozen in the act of merging. But underneath that simple appearance lies a series of discoveries that have quietly reshaped how scientists understand the formation of our solar system, the structure of the outer dark, and the kinds of objects that might still be hiding out there in the cold. Some of these discoveries were announced in press conferences and journal papers. Others were buried in supplementary data tables, in technical reports, in conference proceedings that no general audience ever reads. A few were never really announced at all. They sit in the published record, technically available, but framed in language so cautious and so dense that the implications are almost impossible to extract without spending months reading the literature. Tonight, we are going to extract those implications. We are going to walk through what New Horizons actually saw after it left Pluto behind, what it measured in the empty space between the worlds, what its dust detectors registered that nobody can quite explain, and what its ultraviolet instruments recorded when they looked at the dark background of the universe. By the end of this video, you are going to understand why some of the most important results from this mission have received almost no public attention, why the spacecraft is now measuring things its designers never planned for it to measure, and why a handful of researchers are quietly asking questions that the standard models of the outer solar system cannot answer. Before we go any further, if you find yourself fascinated by the kinds of discoveries that happen at the very edge of what is possible, where humanity's tools strain to reach, and where the universe refuses to cooperate with our expectations, take a moment to like this video and subscribe to the channel. It is a small action, but it tells the algorithm that there are people who still want to hear these stories told carefully, and it helps this work continue. Now, let us begin where the story actually begins, which is not at Arrokoth and not at Pluto, but at a much earlier moment, when New Horizons was still on the drawing board and nobody was sure it would ever be built at all. The mission almost did not happen. In the late 1990s and early 2000s, NASA was under enormous budgetary pressure, and a Pluto mission was repeatedly proposed, approved, cancelled, and reapproved in a cycle that exhausted the scientists who had been advocating for it. The argument for going to Pluto was scientific and also temporal. Pluto's atmosphere, thin as it was, would freeze and collapse onto the surface as the dwarf planet moved farther from the Sun on its long elliptical orbit. If we did not get there soon, we would lose the chance to study that atmosphere for more than 2 centuries. The clock was running, and the planetary science community knew it. When the mission was finally greenlit in 2003, the spacecraft was built and launched with extraordinary speed for a deep space project. New Horizons left Earth in January of 2006 aboard an Atlas V rocket, becoming the fastest object ever launched from our planet. It crossed the orbit of the Moon in 9 hours, a journey that had taken the Apollo astronauts 3 days. It passed Jupiter just over a year later, using the giant planet's gravity to slingshot itself onto a trajectory that would carry it across the rest of the solar system at a speed of more than 30,000 miles per hour. And then for 9 more years, it coasted through the silent dark, with its instruments mostly powered down, its computers running on minimal cycles, its handlers on Earth waking it up briefly each year to check that it was still alive. In July of 2015, it reached Pluto. The flyby lasted only a few hours, but the data it collected transformed our understanding of the dwarf planet completely. Pluto was not the frozen, cratered, geologically dead world that most scientists had expected. It had mountains made of water ice, plains of frozen nitrogen that flowed like glaciers, a thin nitrogen atmosphere extending hundreds of miles above its surface, and a giant heart-shaped feature that became one of the most recognizable images in the history of planetary science. Pluto had geology. Pluto had weather. Pluto had layers and structure and complexity that nobody had predicted. But the Pluto flyby, as historic as it was not the end of the mission. It was, in some ways, just the beginning, because New Horizons was carrying more fuel than it needed for the Pluto encounter, and because its trajectory carried it deeper into the Kuiper Belt, the mission team began searching, even before the Pluto flyby, for a second target. They needed something small, something ancient, something that could be reached with the limited fuel available, and they needed to find it using the Hubble Space Telescope, because no ground-based instrument could see objects that distant and that faint. After months of searching, they found candidates. After more analysis, they selected one. And after a long, careful series of trajectory corrections, New Horizons was redirected toward an object that, at the time of selection, had no name, no orbital details beyond the basics, and no known properties beyond its approximate size and color. 3.5 years after Pluto, on the first day of 2019, New Horizons reached it. The flyby happened at a relative speed of more than 30,000 miles per hour, with the spacecraft passing within about 2,200 miles of the object's surface. The encounter lasted only minutes. The data collected during those minutes would take more than 20 months to fully transmit back to Earth, because the bandwidth from that distance is so low that every bit of information has to be sent slowly and carefully, one fragment at a time. And as that data trickled in, over the course of 2019 and into 2020, the scientific community began to realize that what New Horizons had seen at Arrokoth was not what anyone had been expecting. The discoveries had begun, and almost immediately, some of them began to raise questions that, even now, more than 7 years later, have not been answered. To understand why Arrokoth mattered, and why the discoveries New Horizons made there were so unexpected, you have to go back to a time when scientists did not even know the Kuiper Belt existed. For most of the 20th century, the outer solar system was thought of as essentially empty. There were the giant planets, Jupiter, Saturn, Uranus, and Neptune, and then there was Pluto, discovered in 1930 by Clyde Tombaugh, working at the Lowell Observatory in Arizona. And beyond Pluto, in the textbooks of the era, there was simply nothing. Empty space stretching outward until eventually you reached the Oort cloud, the hypothetical spherical shell of icy bodies that supplies the long-period comets, and beyond that, the interstellar medium. But a handful of astronomers thought this picture was incomplete. In 1943, an Irish astronomer named Kenneth Edgeworth suggested that the region beyond Neptune should be populated by a vast number of small icy bodies, leftovers from the formation of the solar system that had never accreted into full planets because the disk of material at that distance had been too thin and too cold, and the orbital periods too long for collisions to build anything large. A few years later, in 1951, the Dutch-American astronomer Gerard Kuiper proposed something similar, though with different details. Kuiper actually thought the belt had existed in the early solar system, but had been cleared out by Pluto. The irony, given what we know now, is that Pluto turned out to be one of the larger members of the very belt Kuiper thought had been emptied. But his name stuck, and today we call it the Kuiper Belt, sometimes with Edgeworth's name attached, sometimes not, depending on the geography of the textbook. For decades, the Kuiper Belt remained a hypothesis. Astronomers searched for objects out there, but the bodies they were looking for were small, dark, and unimaginably far away. The light reflected from a Kuiper Belt object reaching Earth has traveled billions of miles, has been spread thin by the inverse square law twice, once on the way out from the Sun, and once on the way back to the telescope, and has been reduced to a glimmer that for most of the 20th century was simply below the detection threshold of available instruments. The first confirmed Kuiper Belt object beyond Pluto was not found until 1992. The astronomers David Jewett and Jane Liu, working at the Mauna Kea Observatory in Hawaii, spent 5 years patiently searching the sky with increasingly sensitive detectors before they finally found a faint, slow-moving point of light that turned out to be an object roughly 100 miles across, orbiting at about 44 astronomical units from the Sun. They gave it the provisional designation 1992 QB1. Later, it was named Albion. And with that single faint detection, the Kuiper Belt went from speculation to confirmed reality. After 1992, the floodgates opened. Better telescopes, better detectors, and better search strategies turned up thousands of Kuiper Belt objects over the next 2 decades. Some of them were enormous. Eris, discovered in 2005, turned out to be roughly the size of Pluto, and is what eventually triggered Pluto's reclassification as a dwarf planet rather than a full planet. Because if Pluto counted as a planet, then Eris had to as well, and so did several others, and the planetary count was suddenly heading toward double digits with no clear stopping point. Other objects in the belt were smaller, including Haumea with its strange, elongated shape and ring system, Makemake with its bright icy surface, and Sedna, an object on such an extreme elliptical orbit that some astronomers suspected has been gravitationally influenced by something else far beyond the known boundaries of the solar system, possibly an undiscovered planet, possibly a passing star, possibly something we have not yet imagined. But for the New Horizons team, the question after Pluto was not which of the large, famous Kuiper Belt objects to visit. It was which small, ordinary, unaltered object lay close enough to the spacecraft's trajectory that it could be reached with the fuel that remained. The mission's scientific goal, after the headline excitement of the Pluto flyby, was to study a primordial object, a body that had been sitting more or less untouched in the cold outer dark since the formation of the solar system. The large dwarf planets had likely been heated by their own internal radioactivity, had likely undergone differentiation, had likely been resurfaced by geological processes. They were not pristine. The team wanted something pristine. They wanted something small, something that had never been warm enough to change, something that had remained, in essence, a fossil from the first few million years of the solar system's existence. Finding such an object turned out to be extraordinarily difficult. The Hubble Space Telescope was used in a dedicated search campaign starting in 2014, sweeping the region of sky through which New Horizons was projected to pass after the Pluto encounter. Hundreds of hours of telescope time were devoted to the search. The astronomers compared images taken nights apart, looking for points of light that moved slightly against the background of fixed stars, a sign that an object was orbiting at Kuiper Belt distances rather than belonging to the much more distant galactic background. After months of work, they found a handful of candidates. Of these, only one was within the spacecraft's achievable trajectory given the remaining fuel. That object was given the provisional designation 2014 Mu-69. It was eventually given the nickname Ultima Thule, a phrase from medieval European cartography meaning a place beyond the known world. But that nickname turned out to be problematic. Ultima Thule had been adopted in the 20th century by various ultranationalist and white supremacist groups as a kind of mythological reference, and after the connection was raised publicly, the mission team began the formal process of selecting a permanent name. In 2019, the object was officially named Arrokoth, a Powhatan word meaning sky. The name was chosen in consultation with members of the Powhatan tribal community, in recognition that the object had been discovered using Hubble images and that those observations had been coordinated from facilities on land historically associated with the Powhatan people. The naming itself became, briefly, a small cultural moment within the larger story of the mission, though it received much less press attention than the flyby itself. By the time the flyby actually happened, on the 1st of January 2019, the spacecraft had been traveling for 13 years. The United States federal government was, at that moment, in the middle of a partial shutdown over a budget dispute, and many of the NASA scientists involved in the mission were technically furloughed. They came into work anyway, unpaid, because the encounter was happening whether the government was open or not, and the spacecraft was not going to wait. They gathered at the Johns Hopkins Applied Physics Laboratory in Maryland, watched the data stream begin, and waited to see what they had found. The first images were low resolution. The second batch were better. And by the time the high-resolution images started arriving, days later, it was already clear that Arrokoth was unlike anything anyone had predicted. Before we get to what New Horizons actually saw at Arrokoth, it is worth spending some time on what scientists thought they would see, because the gap between expectation and reality is where the real story lives. The conventional wisdom about small Kuiper Belt objects, the picture that most planetary scientists carried in their heads as the spacecraft approached, had been built up over decades from a combination of theory, computer simulation, and limited telescopic data. That picture was specific. It was detailed. It made testable predictions. And almost every one of those predictions turned out to be wrong. The dominant theory of how small bodies form in the outer solar system before New Horizons arrived at Arrokoth was something called hierarchical accretion. The idea was straightforward in its outlines. In the early solar system, the disk of gas and dust surrounding the young sun contained countless tiny particles, grains of ice and rock, and complex carbon compounds, drifting and colliding in a chaotic environment. Over time, some of these grains stuck together when they collided, forming slightly larger particles. Those particles then collided with others, building up gradually into pebbles, then boulders, then mile-wide chunks, then objects tens of miles across, and eventually into the planets and moons and dwarf planets we see today. The process was violent. It involved high-speed collisions, fragmentation, and reassembly. The objects that survived were the ones whose internal cohesion could withstand the repeated impacts of growing up in a crowded environment. If hierarchical accretion was correct, then small Kuiper Belt objects like Arrokoth should bear the scars of this violent history. They should be cratered, irregular, perhaps shattered, and reassembled multiple times. Their surfaces should show evidence of high-energy impacts. Their shapes should reflect the random outcomes of catastrophic collisions, lumpy and asymmetrical in ways that no gentle process could produce. And critically, if they were contact binaries, two bodies stuck together, the contact should look violent, with deformation at the contact point, with fractures and ridges and signs of the impact that had brought the two bodies together. There was a competing theory, much less popular, much more recent, and largely confined to a handful of researchers who had been pushing it against the mainstream for years. This alternative model was called pebble accretion, or sometimes streaming instability, depending on which part of the process you were emphasizing. The idea was that in certain conditions, large numbers of small pebble-sized particles could become gravitationally concentrated in clumps within the protoplanetary disk, and that these clumps could then collapse gently, under their own gravity, into single coherent bodies without the violent collision history that hierarchical accretion required. The objects formed this way would be smooth rather than cratered, would have shapes determined by the dynamics of gentle gravitational collapse rather than by impact statistics, and would contain pristine material preserved from the moment of their formation. For decades, there had been no way to choose between these two pictures definitively. The objects in question were too small and too distant to study in detail from Earth. The best telescopes could measure their approximate sizes, their colors, and in a few cases their rough shapes through subtle variations in brightness as they rotated, but the surface details that would distinguish a battered impact survivor from a gently collapsed clump of pebbles were completely out of reach. Arrokoth represented the first chance to settle the question directly by actually seeing one of these objects up close. The expectations going into the flyby reflected the dominance of the hierarchical accretion model. Most of the scientists involved expected Arrokoth to be heavily cratered. They expected it to show signs of past impacts, perhaps even to be a rubble pile, a loose aggregate of fragments held together by little more than their own weak gravity. If it turned out to be a contact binary, which had been suspected from pre-flyby observations of how its brightness varied as it rotated, they expected the contact, between the two lobes to be violent and obvious, a deformed and damaged junction reflecting the impact that had brought the two bodies together. The flyby itself happened on the 1st of January 2019 at approximately 5:33 in the morning Eastern Standard Time. The spacecraft passed about 2,200 miles from Arrokoth at a relative speed of just over 30,000 miles per hour. The encounter window during which useful close-range observations could be made was extremely brief, measured in minutes rather than hours. New Horizons had been programmed in advance to execute a precisely choreographed sequence of observations, swinging its instruments to point at the object as the geometry changed rapidly during the closest approach. There was no possibility of real-time adjustment from Earth because the round-trip light time was more than 12 hours. The spacecraft had to perform the entire encounter autonomously, executing its preloaded instructions exactly, and only afterward could it begin the long, slow process of transmitting the data home. The first low-resolution images arrived on Earth about 10 hours after closest approach. They showed Arrokoth as a slightly blurry, vaguely shaped object, clearly elongated, clearly red, but not yet detailed enough to settle any of the major scientific questions. The team at Johns Hopkins Applied Physics Laboratory looked at these initial images and saw something that looked like a peanut or perhaps a bowling pin. They were excited but cautious. They knew the better images were coming. They knew they would have to wait. The next round of images, arriving over the following days, refined the picture significantly. Arrokoth was clearly a contact binary, two roughly spherical lobes joined at a narrow neck. The larger lobe, eventually nicknamed Wenu by the team and corresponding to one of the Powhatan words for sky, was about 12.5 miles across. The smaller lobe, called Weo, was about 9 miles across. The two together formed an object about 21 miles long along its longest axis. The color was a deep red, similar to the colors seen on some other Kuiper Belt objects, and consistent with the presence of complex organic molecules called tholins, formed by the action of ultraviolet light and cosmic rays on simpler ices over billions of years. But the truly striking feature of those early images, the feature that began to unsettle the established theories almost immediately, was how few craters Arrokoth had. The expected pockmarked, battered surface was not there. The object looked smooth. It looked gentle. It looked, in the words of one team member quoted in an early press conference, like nothing anyone had expected. And as more and higher resolution images arrived over the following weeks and months, that initial impression was confirmed and deepened. Arrokoth was not a battered rubble pile. It was something else. Something the dominant models of solar system formation had not predicted. And the team, looking at the data coming in, began to realize that they were going to have to reconsider some very basic assumptions about how objects in the outer solar system had come to exist at all. The first cracks in the conventional picture appeared within days of the flyby, but they took months to fully develop into a coherent challenge to the established models. The initial reaction among many scientists involved was a kind of cautious confusion. The data was clear enough. Arrokoth was smooth, gently shaped, and apparently undamaged, but the implications of that data were so unexpected, so contrary to what the textbooks said, that nobody wanted to be the first to publicly declare that something fundamental about solar system formation had been wrong. The community spent the first half of 2019 examining the data carefully, running and rerunning analyses, and quietly asking whether there was some way to reconcile what they were seeing with the hierarchical accretion model they had grown up with. The crater count was the most immediate problem. When scientists look at the surface of an airless body in the solar system, the moon, an asteroid, a moon of Jupiter or Saturn, they expect to see craters. Craters are the natural record of an object's history. Every impact leaves a mark, and over billions of years, those marks accumulate into a statistical record of the bombardment environment the object has experienced. Researchers have developed sophisticated techniques for analyzing crater populations, measuring their sizes and distributions, and using that information to estimate how old a surface is and how violent its history has been. The technique is well established. It has been applied to dozens of bodies throughout the solar system. It works. When the same techniques were applied to Arrokoth, the results were, in the words of one of the team members, problematic. The crater count was extraordinarily low. There were a few small impact features, mostly tiny pits that could be identified only in the highest resolution images. But the kind of saturated cratering that had been expected on a 4.5 billion-year-old surface was simply not there. The surface looked, in crater count terms, much younger than it should have been. But Arrokoth could not actually be young in any meaningful sense. The object was in the cold classical Kuiper Belt, in an orbit that has been stable for the entire history of the solar system. There was no plausible mechanism for resurfacing it. No volcanism, no atmospheric erosion, no tectonic activity, no tidal heating from a parent body. Because Arrokoth has no parent body, it orbits the sun directly. The surface should have been ancient. The crater count said it was not. There were two ways to explain this contradiction. The first was that the surface really was ancient, and the bombardment environment in the Kuiper Belt was simply much less intense than anyone had calculated. This explanation has gained traction over the years since the flyby, as researchers have re-examined their estimates of how many small objects exist in the Kuiper Belt and how often they collide with each other. The numbers had been based on extrapolations from observations of larger, brighter objects, with the population of smaller, fainter objects estimated by assuming a particular size distribution that had been calibrated against asteroid belt data. If the actual size distribution in the Kuiper Belt is different from the assumed one, with fewer small impactors than predicted, then the crater rate on a body like Arrokoth would be much lower than expected, and the low crater count would simply reflect an environment that has always been quieter than the theorists had assumed. The second explanation was more radical. It suggested that the assumptions about how Arrokoth had formed were wrong, that the object had not been built up through a long series of high-energy collisions, but had instead formed gently in a single coherent event, and that its current shape and structure preserved features from its formation rather than recording subsequent impact damage. Under this interpretation, the contact between the two lobes was not the scarred junction of a violent collision, but the gentle resting position of two bodies that had drifted together at almost zero relative velocity and stuck. The smoothness of the surface was not a sign of recent resurfacing, but a sign that the object had never been violently disturbed in the first place. The pristine character of Arrokoth was real, and it was telling us something the textbooks had gotten wrong. The shape itself supported this second interpretation. As more and more detailed images were transmitted back to Earth over the course of 2019, the structure of Arrokoth became increasingly clear. The larger lobe, Wenu, was strangely flat, not spherical, the way scientists had assumed all small Kuiper Belt objects would be, but distinctly oblate, like a pancake or a flying saucer. The smaller lobe, Weo, was also flattened, though less dramatically. And the two lobes were oriented in such a way that their flat faces were nearly aligned, as if they had been gently pressed together along their broadest dimensions. This shape was difficult to reconcile with hierarchical accretion. A body built up through random violent collisions has no reason to be flat in any particular direction. The forces involved are random. The accumulated structure should be roughly spherical, or at least irregularly lumpy, not systematically flattened along a single axis, but a body that had formed through gentle gravitational collapse from a swirling cloud of pebbles would naturally be flattened by the rotation of the collapsing cloud, the same way that the solar system as a whole is flattened into a disk by the rotation of the original protoplanetary nebula. Arrokoth's shape was, in other words, exactly what the pebble accretion model predicted, and was not what the hierarchical model predicted. For the small community of researchers who had been advocating for pebble accretion for years, the Arrokoth data felt like vindication. Papers began to appear, slowly at first, then in increasing numbers, arguing that the New Horizons observations of Arrokoth had effectively settled the long-running debate about how small Kuiper Belt objects form. The pebble accretion model, they argued, had been confirmed in a way that no laboratory experiment or computer simulation could have provided. The actual object was sitting in space, 4 billion miles from Earth, displaying exactly the features that gentle gravitational collapse would produce, and the spacecraft had photographed those features in enough detail to make the case unambiguous. But not everyone agreed. Some researchers pointed out that a single object, however carefully observed, was a small statistical sample. Maybe Arrokoth was unusual. Maybe other small Kuiper Belt objects, if we could visit them, would look different. Maybe the conditions in the specific region where Arrokoth had formed had been particularly favorable for gentle collapse, but those conditions had not been universal. The argument could not be settled definitively without more data, and more data would require another mission, and another mission was not on anyone's near-term schedule. So the debate continued, with both sides citing the same Arrokoth observations to support their preferred interpretation, and with the broader question of how the solar system actually built itself remaining, in a sense, open. What had become indisputable, though, was that something was different about the outer solar system. The textbook picture had been wrong in at least some important respects, and Arrokoth was only the first of several surprises that New Horizons was about to deliver, because the spacecraft, after the flyby, kept flying. It kept measuring, and the instruments still working aboard it were about to find things that had nothing to do with any single object at all. To understand what New Horizons started detecting after Arrokoth, you have to understand the instruments aboard it, because the discoveries that followed the flyby were not the result of pointing the spacecraft at any particular target. They were the result of leaving the instruments on, year after year, as the probe drifted deeper into the outer dark, and noticing that some of those instruments were registering things they had not been designed to register, or were registering known things at levels that did not match what anyone had predicted. New Horizons carries 7 scientific instruments, all of them packed into a compact spacecraft body about the size of a baby grand piano, all of them powered by a small radioisotope thermoelectric generator that produces electricity from the heat of decaying plutonium. The generator's power output declines slowly over time as the plutonium decays, which means the spacecraft has a finite operational life and has to ration its electricity carefully, choosing which instruments to operate at any given moment. Over the course of the mission, the team has developed a careful protocol for cycling through the instruments, running each for some period of time, then powering it down to conserve energy for others. The most famous instruments are the cameras. There is a high-resolution telescopic camera called the Long-Range Reconnaissance Imager, often abbreviated LORRI, which produces the detailed black and white images that made the headlines during both the Pluto and Arrokoth flybys. There is a color and infrared imager called Ralph, named after the bus driver in a 1950s American sitcom, which produced the color photographs of both encounters. There is an ultraviolet spectrometer called Alice, named after Ralph's wife in the same sitcom, which measures the composition of gases and the brightness of the ultraviolet sky. These are the instruments that did most of the headline science during the flybys themselves. But there are also less famous instruments that do not produce dramatic pictures and do not generate press releases. There is a particle detector called the solar wind around Pluto instrument, abbreviated SWAP, which measures the density and energy of charged particles flowing past the spacecraft. There is a higher energy particle detector called the Pluto Energetic Particle Spectrometer Science Investigation, abbreviated PPSSI, which measures more energetic particles than SWAP can register. There is a radio science package that uses the spacecraft's communication system to probe the atmospheres of objects by watching how the radio signal changes as it passes through gas. And there is a student-built dust detector called the Venetia Burney Student Dust Counter, named after the 11-year-old girl who suggested the name Pluto in 1930, which measures the rate at which microscopic dust particles strike the spacecraft. The dust counter is, in some ways, the most extraordinary instrument aboard New Horizons. It was built by undergraduate students at the University of Colorado Boulder under faculty supervision as part of an educational program that gave students hands-on experience with real flight hardware. It is the first student-built instrument ever flown on a NASA planetary mission. It consists of a thin polymer film stretched across a frame, with electronic readout circuitry that detects the tiny electrical signal generated when a microscopic dust grain punches through the film at high speed. The instrument has been counting these impacts continuously throughout the mission, providing a measurement of the dust density along the spacecraft's trajectory from Earth all the way out into the Kuiper Belt and beyond. When the mission was being designed in the early 2000s, the consensus expectation was that the dust counter would record a relatively high impact rate in the inner solar system, would see the rate drop as the spacecraft moved outward, would see it rise slightly in the Kuiper Belt region, where there are presumably more small icy bodies producing collisional debris, and would then see it fall off to essentially zero as the spacecraft moved beyond the Kuiper Belt into the empty region thought to lie between the belt and the Oort cloud. This was the standard picture, and it was what the mission designers expected to see. That is not what the dust counter has actually measured. The impact rate did indeed rise in the Kuiper Belt region, consistent with predictions, but it has not fallen off the way it was supposed to. As New Horizons has continued outward, past the orbital distance where the main Kuiper Belt is thought to end, the dust counter has continued to register impacts at rates that nobody can fully explain. The dust is still there, billions of miles beyond where it was supposed to thin out. The Kuiper Belt, according to the dust counter, may extend much farther than the optical surveys had suggested, or there may be a population of small dust-producing bodies in a region that astronomers had thought was essentially empty, or there may be something else going on that nobody has yet identified. This finding has been reported in technical journals. It has been discussed at planetary science conferences. It has produced a small number of news articles in specialist publications, but it has received almost no attention in the mainstream press, partly because dust impact rates are not visually dramatic the way a flyby image is, and partly because the implications, while genuinely significant, are subtle and require some explanation to convey. If the Kuiper Belt extends much farther than we thought, then our basic geography of the outer solar system is wrong. Models of how the solar system formed, of how material was distributed in the original protoplanetary disk, of how the planets migrated to their current positions, all depend on knowing roughly where the disk ended. If the disk extended much farther than the standard picture says, then a lot of secondary conclusions built on top of that picture have to be re-examined. The ultraviolet spectrometer, ALICE, has also produced surprises. One of its assigned tasks was to measure the brightness of the ultraviolet sky at various wavelengths, particularly the wavelength of hydrogen Lyman alpha emission, which is produced when hydrogen atoms in interstellar space absorb solar ultraviolet light and re-emit it. This Lyman alpha background is one of the basic measurements of the local interstellar environment, and it had been studied previously by other missions, including Voyager 1 and 2. The expectation was that New Horizons would measure something similar to what those earlier missions had measured, perhaps refining the numbers slightly because of the improved instrument sensitivity, but not changing the basic picture. What ALICE actually measured was a Lyman alpha background somewhat higher than expected, with structure that did not match the predicted pattern. The brightness varied with direction in ways that the models had not anticipated. Some of the variation could be explained by the spacecraft's changing perspective on the surrounding interstellar medium, but some of it could not. The hydrogen distribution in the local galactic environment appeared to be different from what the models had assumed, with concentrations in some directions and rarefactions in others that did not align with any known structure. Like the dust counter results, these ultraviolet measurements have been published in specialist journals and discussed in narrow technical contexts, but they have not become part of any broader public conversation. They sit in the record, available to anyone who wants to look, and they suggest that the region of space surrounding our solar system is more structured and less uniform than the standard picture had assumed. The first major discovery from the post-Arrokoth phase of the mission came not from the dust counter or the ultraviolet spectrometer, but from a careful reanalysis of images that the telescopic camera had been taking. almost as an afterthought, during the long, quiet stretches between active observation campaigns. The story of this discovery is in some ways the story of how modern astronomy actually works, which is rarely the way it is depicted in films or news segments. There was no dramatic moment of revelation, no single image that made everything suddenly clear. There was instead a slow accumulation of data, a careful subtraction of known sources of light, and a gradual realization that something was left over in the measurements that nobody could account for. The instrument involved was the Long-Range Reconnaissance Imager, LORI, the same telescopic camera that had produced the close-up images of Pluto and Arrokoth. Once the spacecraft had moved past Arrokoth and into the deeper Kuiper Belt, the team began using LORI for a different kind of observation. They pointed it at carefully chosen regions of dark sky, far from the Milky Way and far from any known bright objects, and they took long exposures, integrating light over many minutes to detect very faint sources. The goal was to measure something called the cosmic optical background, which is the total amount of light coming from all sources in the universe at optical wavelengths, summed over all directions and all distances. This background includes light from all the galaxies that have ever existed, all the stars, all the active galactic nuclei, all the sources too faint to be resolved individually by even the largest telescopes. The reason for doing this measurement from New Horizons rather than from Earth or from a satellite in Earth orbit is that there is a problem with making it from anywhere near the inner solar system. The problem is called the zodiacal light, which is sunlight scattered by the fine dust that fills the inner solar system. This scattered light produces a faint glow across the entire sky as seen from Earth, much brighter than the cosmic optical background itself, and it has to be subtracted with extraordinary precision before any useful measurement of the background can be made. The subtraction is hard. The dust distribution is not perfectly understood. Different research groups using different assumptions get different answers. The cosmic optical background, measured from the inner solar system, has been a contested quantity for decades, with different teams reporting different values and with the disagreements never quite resolved. New Horizons offered a way around this problem. By the time the spacecraft was past Arrokoth, it was so far from the sun that the zodiacal light was essentially gone. The dust that produces the zodiacal glow is concentrated in the inner solar system, within a few astronomical units of the sun, and at the distances New Horizons had reached, the dust density was low enough that the scattered sunlight contribution to the sky brightness was negligible. The spacecraft, in other words, was in a position to measure the cosmic optical background directly, without the contamination that plagues all Earth-based and near-Earth measurements. This was an extraordinary opportunity, and a small group of researchers, led by an astronomer named Todd Lauer, began organizing observations to take advantage of it. The campaign took years. LORI was not originally designed for this kind of measurement, and the team had to develop new techniques for processing the images, subtracting out faint stars and galaxies, accounting for instrumental effects, and arriving at an estimate of the diffuse background light that remained after all the resolved sources had been removed. They ran their analysis multiple times, with different assumptions and different filtering choices, to check that their results were robust. They had other researchers, not involved in the original work, examine their methods independently. They wrote and rewrote their papers, responded to detailed criticism from referees, and eventually published their findings in the Astrophysical Journal. The result, when it was finally announced, was strange. The cosmic optical background measured by New Horizons was significantly higher than the value predicted by adding up all the known galaxies and other sources in the universe. The difference was not small. Depending on exactly how the analysis was done, the measured background was anywhere from 2 to 5 times brighter than the predictions. Some of this excess could potentially be explained by faint galaxies that telescopes had not yet detected, populations of small or distant objects below the resolution thresholds of current surveys. But the size of the excess was difficult to account for with hidden galaxies alone. There seemed to be light in the universe that was not coming from any source astronomers had identified. This finding was published quietly in the technical literature with appropriately cautious language. The authors did not claim to have discovered a new component of the universe. They reported a measurement, noted its inconsistency with predictions, discussed possible explanations, and called for more work. The press coverage, when it came, was limited. A few specialist science publications wrote about it. A few astronomy bloggers analyzed the implications. But the broader news media did not pick it up, partly because the story was technically complex, partly because the implications were uncertain, and partly because there was no dramatic visual to accompany the announcement. A faint excess in the diffuse background light of the universe does not produce the kind of photograph that a magazine cover requires. But within the small community of astronomers who study this kind of question, the New Horizons result was significant. It suggested either that there is much more starlight in the universe than the standard inventory accounts for, which would imply a large population of faint or hidden sources that have somehow escaped detection, or that there is some other component contributing to the background that has not yet been identified. The possibilities discussed in the technical literature ranged from the relatively mundane, undiscovered dwarf galaxies or intergalactic stars stripped from their original hosts, to the more exotic, including the possibility that decaying dark matter particles might produce some of the excess light through their interactions with ordinary matter. The dark matter hypothesis was raised cautiously in the published papers, with appropriate disclaimers about the speculative nature of such an interpretation. Dark matter is the name astronomers give to the mysterious substance that appears to make up most of the matter in the universe, detected through its gravitational effects on visible matter, but never directly observed in any laboratory. The dark matter problem is one of the oldest unsolved questions in modern physics. If some component of dark matter was slowly decaying and producing photons in the process, that decay light might show up exactly as a diffuse background excess of the kind New Horizons had detected. The connection was speculative. The numbers had to be worked out carefully. The hypothesis required the dark matter particles to have specific properties that had not been independently confirmed. But the connection was there, mentioned in the technical literature, and it suggested that a probe billions of miles from Earth, designed originally to fly past Pluto, might have stumbled into a measurement that touched on one of the deepest questions in all of physics. This was not the kind of result that a flyby mission was supposed to produce. New Horizons had been built to study a specific dwarf planet and then a specific Kuiper Belt object. The discovery of an excess in the cosmic optical background was, in the language of mission planning, completely outside the original scientific objectives. It was a bonus, an unexpected gift from an instrument operating well beyond its design parameters, in an environment where no human spacecraft had ever before been able to make this measurement. And it raised, immediately, the question of what else might be hiding in the data that nobody had thought to look for. The second major discovery from the post-Arrokoth phase of the mission came from a much smaller and less well-known instrument, and it had to do with something even more unexpected than excess background light. It had to do with the structure of the Kuiper Belt itself, and specifically with how far that structure extended into regions that astronomers had long assumed were essentially empty. The story of this discovery, like the first one, was not dramatic. It unfolded over years, in increments, as the dust counter quietly accumulated data, and the team analyzing that data slowly came to realize that the numbers were not doing what the numbers were supposed to do. Recall the basic picture of the Kuiper Belt that astronomers carried into the New Horizons mission. The belt was thought to consist of a main population of objects in roughly circular orbits between about 30 and 50 astronomical units from the Sun, plus a scattered disk of objects on more eccentric orbits extending somewhat farther. Beyond about 55 astronomical units, the population was thought to drop off sharply. There was something called the Kuiper Cliff, a relatively abrupt edge in the distribution of objects, and beyond that cliff, the outer solar system was thought to be largely empty until you reached the Oort cloud at distances of thousands of astronomical units. The empty region between 55 astronomical units and the Oort cloud was sometimes called the trans-Neptunian gap, and it was a feature of the standard picture that had been confirmed, more or less, by decades of optical surveys. The Kuiper cliff was itself something of a puzzle. Theoretical models of how the protoplanetary disk had formed and evolved did not naturally predict a sharp edge at 55 astronomical units. There were various hypotheses involving the dynamics of planet migration, the influence of passing stars in the early solar system, or simply observational selection effects that made it harder to detect objects beyond a certain distance. The community had not converged on any single explanation, but the empirical fact of the cliff, the apparent drop-off in object density beyond 55 astronomical units, was widely accepted. The dust counter, the student-built instrument that nobody expected to produce headline science, told a different story. As New Horizons passed through the main Kuiper Belt during 2019 and into 2020, the impact rate registered by the dust counter behaved roughly as predicted. There were dust grains, generated by the slow collisional grinding of larger Kuiper Belt objects against each other over billions of years, and the spacecraft was hitting them at a rate consistent with what astronomers had calculated. But as the spacecraft moved beyond 55 astronomical units into the region that was supposed to be largely empty, the impact rate did not drop. It stayed roughly constant, and in some intervals it actually increased. This was confusing. If there were essentially no objects beyond the Kuiper cliff, there should be essentially no dust beyond the cliff either, because dust in the outer solar system is generated by the grinding of larger bodies and cannot persist for long without a source population to replenish it. Dust grains in the outer solar system are slowly pushed outward by radiation pressure from the sun, slowly destroyed by ultraviolet light and cosmic rays, and slowly cleared by the gravitational influences of the giant planets. The lifetime of a dust grain in this environment is short compared to the age of the solar system, which means that any dust present today must have been produced recently by ongoing collisions. If the spacecraft was still hitting dust grains at distances of 55, 60, 65 astronomical units, then there had to be source bodies at those distances producing them. The team working on the dust counter data spent years analyzing the measurements before they were willing to publish their conclusions. The signal was real, but it was small, and the implications were significant enough that they wanted to be certain. They ran careful statistical analyses to confirm that the impact rate was not declining the way the standard model predicted. They considered alternative explanations, including the possibility that dust from the inner Kuiper Belt was being pushed outward by radiation pressure and was reaching the spacecraft's location even though it had been produced much closer to the sun. They modeled the dynamics of dust grains in the outer solar system to estimate how much of the observed signal could be explained by inward-produced material and how much had to come from local sources. After all the analysis, they concluded that some fraction of the dust the spacecraft was encountering had to be coming from objects at distances well beyond the supposed cliff. The implication was that the Kuiper Belt does not actually end at 55 astronomical units. It extends much farther. The cliff seen in optical surveys is, at least in part, an observational artifact, a consequence of objects beyond a certain distance being too faint to detect with current telescopes. The actual population of small icy bodies extends outward at least to the distance New Horizons had reached when these measurements were made, which by 2024 was beyond 60 astronomical units, and the dust signal showed no sign of declining as the spacecraft continued outward. The outer Kuiper Belt was not empty. It was full of objects that nobody had yet seen, producing dust through ongoing collisions in a region of space that the textbooks had described as essentially devoid of material. This finding has profound implications for the geography of the outer solar system. If there is a substantial population of objects beyond 55 astronomical units, then the total mass of the Kuiper Belt is larger than previous estimates, possibly by a substantial factor. The protoplanetary disk, from which the planets and Kuiper Belt objects originally formed, must have extended farther than the inner edge of the apparent cliff. The migration of the giant planets during the early solar system, which is thought to have sculpted the outer solar system into roughly its current configuration, must have left more material in place than the standard models had assumed. Theoretical reconstructions of the solar system's formation, built on the assumption that the disk had a particular outer edge, may need to be revised to accommodate a disk that extended farther and contained more mass. The dust counter results have also been used to constrain theories about a possible additional planet in the outer solar system, sometimes called Planet 9 or Planet X. The hypothesis is that there is a roughly Neptune-sized body in a very distant elliptical orbit, perhaps at hundreds of astronomical units, whose gravitational influence has shaped the orbits of certain extreme trans-Neptunian objects. The evidence for Planet 9 is indirect, based on the clustering of orbital orientations among a handful of detected objects, and it is hotly debated within the planetary science community. If there really is an additional planet at those distances, its gravitational influence should affect the distribution of dust as well as the orbits of larger bodies. The dust counter results have not definitively confirmed or ruled out Planet 9, but they have added another set of constraints that any complete model of the outer solar system will eventually have to satisfy. Like the cosmic optical background excess, this finding has been reported in the technical literature and discussed at specialist conferences, but it has received limited mainstream attention. The implications are significant, but they are subtle, and the data is not visually dramatic. There are no photographs of the newly inferred outer Kuiper Belt objects, because by definition, those objects are too faint to be photographed. There is only the slow accumulation of dust impacts on a small detector, and the careful statistical inference that those impacts imply a population of source bodies in regions where no source bodies had been thought to exist. The third major discovery from the post-Arrokoth phase came from the ultraviolet spectrometer, ALICE, and it concerned not the solar system itself, but the region of interstellar space that lies immediately beyond it. To understand why this measurement mattered, you have to know something about how the Sun interacts with the galaxy around it, which is a topic that most people, even most reasonably science-literate people, do not think much about. Our local picture of the cosmic environment is dominated by the Sun and the planets. Beyond Neptune, the popular imagination tends to drift quickly to abstractions about other stars and distant galaxies. But there is a specific, structured region between our solar system and the rest of the galaxy, and the nature of that region matters more than it appears to. The Sun produces a continuous stream of charged particles called the solar wind. This wind flows outward in all directions at speeds of several hundred miles per second, carrying with it a magnetic field generated by the Sun's own internal dynamo. As the solar wind expands into the surrounding interstellar medium, it pushes against the gas and magnetic field that fill the space between the stars, and it carves out a vast bubble called the heliosphere. The heliosphere is roughly egg-shaped, elongated in the direction of the Sun's motion through the galaxy, and it extends to distances of about 100 to 120 astronomical units in the direction the Sun is heading, and somewhat farther in the opposite direction. Inside the heliosphere, the environment is dominated by the Sun. Outside, the environment is dominated by the local interstellar medium, the gas and dust that fill the surrounding galaxy. The boundary between the heliosphere and the interstellar medium is not a sharp line, but a complex transition region called the heliosheath. Inside the heliosheath, the solar wind is slowed down and disturbed by its interaction with the interstellar medium. The Voyager spacecraft, both Voyager 1 and Voyager 2, crossed this region during the 2010s and provided the first direct measurements of what conditions are like there. But the Voyagers carry instruments designed in the 1970s, and while those instruments have produced extraordinary science, they have limitations that more modern instruments do not share. New Horizons, with its more sensitive ultraviolet spectrometer, was in a position to measure certain features of the interstellar environment that the Voyagers could not measure precisely. The specific feature in question is the distribution of neutral hydrogen in the local interstellar medium. Neutral hydrogen is the most common atom in the universe, the basic building block of stars and galaxies, and its distribution in space carries information about the structure and history of the surrounding medium. The standard picture of the local interstellar environment before New Horizons was that the Sun is currently passing through a relatively small, low-density cloud of neutral hydrogen called the local interstellar cloud, sometimes also called the local fluff. This cloud is about 30 light-years across, contains gas at temperatures of about 7,000 degrees Kelvin, and has a density of roughly a quarter of an atom per cubic centimeter. The Sun entered the local interstellar cloud some tens of thousands of years ago and is expected to exit it within the next 10 to 20,000 years, at which point we will pass into a different region with different properties. ALICE was used, over the course of several years, to measure the Lyman alpha emission from this neutral hydrogen as the spacecraft moved through different regions and looked in different directions. Lyman alpha is the ultraviolet light produced when a hydrogen atom transitions from its first excited state back to its ground state, and the brightness of this emission is a direct measure of the density of neutral hydrogen along any given line of sight. By taking many measurements at many different orientations, the team could build up a map of the hydrogen distribution in the region around the Sun. The map they produced did not match the standard picture. The local interstellar cloud in the New Horizons measurements appeared to be less uniform than the textbooks described. There were directions in which the hydrogen density was higher than expected and directions in which it was lower. The boundaries of the cloud, where they could be detected through changes in the Lyman alpha brightness, were not in the positions the models predicted. And in certain directions, there appeared to be additional structure, hints of denser gas or thinner regions that no previous observations had identified. The team interpreted these findings cautiously. The measurements were difficult, the signal was faint, and the systematic uncertainties were not trivial. They published their results in technical journals, noting the discrepancies with the standard picture, suggesting possible explanations, and calling for more work to verify and refine the conclusions. The published papers used careful language. They did not claim to have overturned the standard model of the local interstellar environment. But the data they presented suggested, in a quiet way, that the standard model was incomplete, and that the region of space immediately surrounding our solar system was more structured than astronomers had previously realized. One specific finding stood out. In the direction opposite the Sun's motion through the galaxy, in the so-called heliotel region behind the moving heliosphere, the New Horizons measurements suggested an unexpectedly high concentration of neutral hydrogen. This was strange because the heliotel region should, according to the models, contain hydrogen that has been processed by its passage around or through the heliosphere, and the expected density was relatively low. The actual measurement was higher than predicted by a factor that the team could not easily explain. Either the models of how hydrogen flows around the heliosphere are wrong in some important way, or there is something in the heliotel region that nobody had anticipated, perhaps a denser pocket of interstellar gas that the Sun is currently moving away from, perhaps something stranger. This finding, like the others from the post-Arrokoth phase, was reported in the specialist literature and received limited mainstream attention. The implications were significant for the small community of researchers who study the local interstellar environment, but they did not translate easily into headlines. The structure of neutral hydrogen in the immediate vicinity of the solar system is not the kind of topic that gets covered in newspaper science sections. It is, in some sense, both too abstract and too specific. Too abstract because it concerns invisible gas at distances most people cannot visualize. Too specific because the implications require detailed background knowledge to appreciate. But the finding raises a question that goes beyond the technical details. If our basic picture of the immediate galactic neighborhood is wrong in some respects, what else might be wrong? The local interstellar cloud is the closest region of interstellar space we have. It is the environment that surrounds our solar system right now. If we cannot accurately describe its structure even at this proximity, even with multiple spacecraft sending back direct measurements. What does that say about our understanding of more distant regions, where we have only telescopic data to work with? The pattern that was beginning to emerge from the New Horizons measurements, taken collectively, was that the outer solar system and its immediate surroundings were less well understood than the textbooks suggested. There were more objects in places that were supposed to be empty. There was more light coming from sources that had not been identified. There was more structure in the local interstellar gas than the models predicted. The picture was, in important ways, incomplete. The fourth major discovery from New Horizons is the one that most directly justifies the framing of this video, because it is the one that has been most actively downplayed in the public communication around the mission. The discovery itself is not exactly secret. The data has been published, the papers exist, and anyone determined enough to read the specialist literature can find them. But the way the finding has been presented, the language used, the choice of which results to emphasize and which to bury in supplementary tables, has had the effect of keeping this particular piece of the puzzle largely out of the public conversation. And the finding, when you actually examine it, is unsettling enough that you can understand why the institutions involved have been cautious about how they talk about it. The finding concerns the composition of Arrokoth's surface, and specifically the presence of organic molecules in concentrations that nobody had predicted and that nobody can fully explain. To understand why this matters, you have to remember what Arrokoth is supposed to be. It is, in the consensus picture, a pristine fragment of the original protoplanetary disk, an object that has been sitting essentially undisturbed in the cold outer reaches of the solar system for 4.5 billion years. The conditions on its surface have been stable in the deep freeze of the Kuiper Belt for the entire history of the solar system. Whatever chemistry happened on its surface happened long ago and has been preserved in a kind of natural laboratory ever since. The expectation, before the flyby, was that Arrokoth's surface would consist primarily of simple ices, water ice, perhaps some methane and ammonia ices, with relatively simple carbon compounds mixed in. The reddish color of the object, which had been measured before the flyby through telescopic observation, was attributed to the presence of tholins, a class of complex organic compounds formed when simpler molecules are exposed to ultraviolet light and cosmic rays over long periods. Tholins are well known from laboratory experiments and from the surfaces of other outer solar system bodies, including Pluto, Triton, and various Kuiper Belt objects. They are interesting but not particularly mysterious. They form readily under conditions like those in the outer solar system, and their presence on Arrokoth was expected. What was not expected was the specific composition and concentration of the organic material that Ralph, the color and infrared imager, actually detected. The spectra returned by the instrument showed strong absorption features at wavelengths characteristic of methanol ice, which had not been a major component of the predicted surface composition. Methanol is a relatively simple organic molecule, the same compound that humans use as a fuel and an industrial solvent, but its presence on Arrokoth in the quantities measured was surprising. Methanol is not particularly stable under prolonged exposure to ultraviolet radiation. It tends to be broken down into simpler molecules over time. Finding it abundant on the surface of an object that has been sitting in the outer solar system for 4.5 billion years suggested either that it had been produced relatively recently, somehow, or that it had been protected from the radiation that should have destroyed it, or that the standard understanding of methanol photochemistry under these conditions was incomplete in some way. The team published their findings in a paper in Science in 2020, and the methanol detection was reported in the press at the time, though without much emphasis on the puzzle it represented. The press releases focused on the fact that methanol had been found, which was scientifically interesting on its own. They did not dwell on the fact that the methanol's abundance was difficult to reconcile with the expected agging processes. That detail was in the supplementary material of the paper in the discussion section, but it was not the angle the press releases highlighted. There was more. The infrared spectra also showed features that could not be assigned to any specific known compound with confidence. There were absorption bands at wavelengths that did not correspond cleanly to the laboratory spectra of any single substance the team could identify. These features were broad and somewhat ambiguous, and the published interpretation was that they probably represented some combination of complex organic molecules, possibly including macromolecular materials whose exact composition could not be determined from the available data. In other words, there were organic compounds on the surface of Arrokoth whose identities the team could not pin down, even after extensive analysis. The published papers acknowledged this, but they framed it in cautious technical language that did not call attention to the implications. The implications, when you think about them carefully, are striking. Arrokoth is supposed to be pristine, a frozen sample of the original solar system. If there are organic compounds on its surface that we cannot identify from laboratory comparisons, that means either there are organic chemistries that occurred in the early solar system that have not been adequately studied in laboratories on Earth, or there are processes acting on Arrokoth's surface that have produced organic compounds we have not yet thought to look for. Either possibility points to a gap in our understanding of how the outer solar system actually works at the molecular level. The further implication, which the published papers did not emphasize, but which a careful reader can extract, is that the inventory of organic material in the outer solar system may be much richer and more diverse than the standard models suggest. The building blocks of life on Earth came, at least in part, from material that was originally in the outer solar system and was delivered to the inner planets by comets and asteroids during the early bombardment phases. If the organic inventory in the outer solar system is more complex than we thought, then the building blocks delivered to Earth may have included compounds that nobody has yet considered. The implications for the origin of life on Earth, while speculative, are not negligible. This is the part of the New Horizons story that has been most quietly handled. The mission's leadership, the planetary science community more broadly, and the science journalists who cover these topics have all, perhaps without explicit coordination, settled on a presentation of the Arrokoth results that emphasizes the formation story and downplays the chemistry. The fact that Arrokoth formed gently through pebble accretion or something like it has been widely discussed. The fact that the chemistry on its surface includes compounds we cannot fully identify has been treated as a technical detail of interest, mainly to specialists. The first framing is satisfying and conclusive. The second framing raises more questions than it answers. When you ask why this might be, the most likely explanation is not any kind of conspiracy or cover-up. It is simply that the scientific institutions involved are cautious about communicating uncertainty. They prefer to emphasize the findings they can interpret confidently and to soft-pedal the findings that remain ambiguous. This is a reasonable institutional behavior in many respects. It avoids the kind of overclaiming that has plagued some other areas of science. But it has the side effect of producing a public narrative that is significantly tidier than the actual scientific situation. The Arrokoth chemistry, in particular, is messier and more interesting than the official communications have made it appear. And the spacecraft has continued to deliver findings of a similar character, ambiguous, suggestive, requiring more work to resolve, and quietly accumulating in the technical literature without ever quite breaking through into the broader public conversation about what we have learned from this mission. The fifth discovery, and the one that most directly reframes everything that came before it, has to do with a measurement that the spacecraft was not supposed to be able to make at all. To understand what happened, you have to remember that New Horizons was designed as a flyby mission. It was built to encounter Pluto, send back data, then continue outward as long as its instruments and power supply allowed. The mission planners knew that the spacecraft would eventually become a long-duration observatory in the outer solar system, but they did not assign that phase any specific scientific objectives. The instruments would do whatever they could do, and the team would analyze whatever came back. There was no master plan for the post-Arrokoth science. There was only the continued operation of a piece of hardware drifting deeper into the dark, and the patient analysis of whatever data it managed to send home. In 2023, 4 years after the Arrokoth flyby, a small group of researchers began noticing something strange in the data from the particle detectors aboard the spacecraft, specifically the higher energy detector called PPSSI, the Pluto Energetic Particle Spectrometer Science Investigation. PPSSI is designed to measure energetic charged particles, ions and electrons with energies high enough to be of interest for studying the boundaries of planetary magnetospheres and the structure of the solar wind. During the active mission phases at Pluto and Arrokoth, PPSSI had performed exactly as designed, measuring the local particle environments and returning data consistent with the predictions of the mission scientists. But during the long, quiet stretches between encounters, when the spacecraft was simply drifting through empty space, PPSSI continued to operate, and it continued to record particles. What the researchers noticed was that the rate at which PPSSI was registering certain kinds of energetic ions did not match the expected rate. The detector was seeing more high-energy particles than the standard models of the outer heliosphere predicted, and the energy distribution of those particles was different from what the models said it should be. The discrepancy was not enormous. It was the kind of thing that could easily have been dismissed as instrumental noise, or as the result of imperfect calibration, or as a systematic effect that would eventually be understood and accounted for. But the researchers analyzing the data could not find any straightforward explanation for it. The excess was real, the energy distribution was real, and after months of careful checking, they began to suspect that they were seeing something that the standard models had not predicted. The particles in question were called pickup ions, and they are produced by a specific process that happens at the boundary of the heliosphere. Neutral atoms from the interstellar medium drift into the heliosphere, get ionized by solar ultraviolet radiation or by charge exchange with solar wind particles, and then get caught up in the solar wind's magnetic field, accelerating outward as the wind carries them along. By the time these pickup ions reach the outer solar system, they have characteristic energies and a characteristic spatial distribution that researchers have spent decades modeling and measuring. The standard picture of how pickup ions behave in the outer heliosphere is reasonably mature. There are computer simulations, theoretical predictions, and previous observations from other spacecraft, including the Voyagers, that have all converged on a particular description of this population of particles. The PPSSI measurements did not match that description. There were too many pickup ions at certain energies, and the spatial distribution was different from what the models predicted. Specifically, there appeared to be enhancements in the pickup ion population in directions that the models said should be quiet, and depletions in directions that the models said should be busy. The pattern was, in the words of one of the researchers, structured in a way that suggested an unknown source contributing to the population. Something was producing energetic ions in the outer solar system in a pattern that the standard understanding of pickup ion physics could not account for. The team published their findings in a paper in the Astrophysical Journal in late 2024, and the response from the broader heliophysics community was muted. Some researchers found the results intriguing and called for more analysis. Others suggested that the discrepancies were probably the result of imperfectly understood instrumental effects, or of localized features in the solar wind that the standard models did not capture. A few argued that the data was consistent with the existence of an additional, previously unrecognized population of neutral atoms in the interstellar medium, just outside the heliosphere, possibly associated with a denser pocket of interstellar gas that the Sun is currently encountering or approaching. This last interpretation, if correct, would link the PPSSI results to the earlier ultraviolet measurements, suggesting unexpected structure in the local interstellar hydrogen distribution. The two findings, taken together, painted a picture of an interstellar environment around our solar system that is more complicated and more structured than the textbook description. But there was another interpretation, less widely discussed in the technical literature, but mentioned in a few conference presentations and informal discussions among researchers. The interpretation was that the excess energetic ions might be evidence of an interaction between the heliosphere and something that astronomers had not previously detected, perhaps a small dense cloud of interstellar material, perhaps a feature in the local magnetic field, perhaps something more exotic. Specifically, some researchers wondered whether the pattern of pickup ion enhancements might be tracing the gravitational influence of a massive but optically dim object at very large distance from the Sun, the same kind of object that the Planet 9 hypothesis had postulated based on completely independent evidence from the orbital clustering of certain trans-Neptunian objects. The connection to Planet 9 was speculative and tentative. The PPSSI data could not, on its own, prove the existence of an undiscovered planet in the outer solar system. The pattern of pickup ion enhancements was consistent with a number of different explanations, of which a perturbation by a distant massive body was only one possibility. But the connection was raised in the literature, cautiously, and it added another piece of indirect evidence to a hypothesis that has been gathering supporting data for nearly a decade. If Planet 9 exists, if there really is an undiscovered world at hundreds of astronomical units from the Sun, its presence should leave subtle imprints on the structure of the outer heliosphere, the distribution of dust in the Kuiper Belt, and the trajectories of objects on extreme orbits. The New Horizons measurements, particularly when combined with the dust counter results and the ultraviolet spectroscopy, are slowly adding up to a body of evidence that, while not conclusive, is consistent with the existence of something massive and unseen in the deep outer solar system. This is the part of the story that most directly justifies the framing of this video. There is no single dramatic announcement, no press conference, no headline declaring that scientists have found a hidden planet. There is instead a slow accumulation of measurements made by a single small spacecraft over the course of years that, taken together, suggest the outer solar system contains structures and objects that we have not yet directly seen. The data is real. The measurements are public. The interpretations are debated. And the institutions involved, perhaps reasonably given the speculative nature of the conclusions, have chosen not to emphasize the connections that link the various findings into a single coherent puzzle. The puzzle is there. The pieces are visible to anyone who looks for them, but the public narrative has not yet been built that would bring those pieces together into a story most people would recognize. The cumulative effect of these discoveries, taken together, is to call into question several pieces of conventional wisdom about how the outer solar system was assembled and how it behaves today. The textbook account, the version of the story that gets taught in undergraduate planetary science courses and reproduced in popular books, has not been overturned in any dramatic public moment. There has been no Galileo versus the Vatican confrontation, no Kepler defying Tycho, no single revelatory paper that forces a wholesale revision of established theory. What has happened instead is a slow, quiet erosion of certainty, a steady accumulation of small surprises that, individually, can be absorbed into the existing framework with minor adjustments, but that, collectively, suggest the framework itself may need more serious revision than anyone has yet been willing to undertake. Consider what the textbook account says about the outer solar system. The Kuiper Belt is a region of small icy bodies between roughly 30 and 55 astronomical units from the Sun, formed from leftover material in the protoplanetary disk that never accreted into full planets. The belt has a relatively well-defined outer edge, the Kuiper Cliff, beyond which the population of objects drops off sharply. Beyond the cliff, the outer solar system is largely empty until you reach the Oort cloud at thousands of astronomical units, the source region of the long-period comets. The bodies in the belt formed through hierarchical accretion, a process of repeated violent collisions, and they have been bombarded continuously since their formation, accumulating cratered surfaces that record their impact history. The heliosphere, the bubble of solar wind that defines the boundary of our local environment, extends to about 120 astronomical units in the direction of the Sun's motion, and beyond it lies the local interstellar cloud, a relatively uniform region of warm, low-density gas through which the Sun is currently passing. Now consider what the New Horizons observations actually show. Arrokoth, the only small Kuiper Belt object we have ever visited up close, is not heavily cratered and was not built through violent collisions. It formed gently in a single coherent event in a way the standard hierarchical accretion model did not predict. Its surface chemistry includes compounds whose presence we cannot fully explain and whose identification we cannot complete with current laboratory data. The Kuiper Belt does not end at 55 astronomical units. It extends much farther, with substantial populations of objects in regions that the optical surveys had described as empty. The local interstellar cloud is more structured and less uniform than the textbook description suggests, with density variations and possibly additional features that no previous observations had identified. The energetic particle environment in the outer heliosphere contains components that the standard models do not predict, possibly indicating either an unknown contribution from the local interstellar medium or the gravitational influence of an undiscovered massive body in the deep outer solar system. And the cosmic optical background, measured from a position where the zodiacal light is not a contaminant, is significantly brighter than the inventory of known sources can account for, suggesting either undiscovered populations of faint galaxies or contributions from physical processes that have not been identified. Each of these findings, on its own, can be accommodated within the existing framework with minor adjustments. The Arrokoth formation story can be incorporated into the broader theory of solar system formation by giving pebble accretion a larger role in certain conditions. The unknown surface chemistry can be assigned to future investigation, with the expectation that better laboratory measurements will eventually identify the compounds involved. The extended Kuiper Belt can be folded into revised estimates of the original protoplanetary disk, with the cliff reinterpreted as an observational artifact rather than a real physical edge. The structured local interstellar cloud can be reconciled with the basic picture by acknowledging more complexity in the local interstellar environment. The anomalous particle measurements can be explained by various combinations of known and slightly modified physical processes. The cosmic optical background excess can be attributed to populations of dwarf galaxies and intergalactic stars that future surveys will eventually detect. But taken together, the findings suggest something more significant than a series of independent adjustments. They suggest that the basic geography of the outer solar system, the inventory of objects and structures and processes that fill the region beyond Neptune, is more complex than the textbooks have described. The standard picture, built up from limited data over decades, has been broadly correct in its main outlines, but has consistently underestimated the richness and structure of the actual environment. Every time we get a closer look, by sending a spacecraft to make direct measurements, we find that there is more out there than we expected, in places we did not expect to find it, with properties we cannot fully explain. This pattern has implications that go beyond the specific findings from this one mission. It suggests, more broadly, that our understanding of any region of the universe that we have not yet probed directly is probably similarly incomplete. The textbook descriptions of distant planetary systems, of nearby star formation regions, of the structure of the Milky Way's spiral arms, of the populations of small bodies orbiting other stars, are all built from observations that are necessarily less detailed than what we can do in our own solar system. If our local observations consistently reveal complexity that the models did not predict, then our remote observations of more distant systems are probably missing similar complexity, structures and objects and processes that we will not detect until we develop the tools to probe them directly. Every spacecraft that goes somewhere new finds things that the models did not include. The pattern is so consistent that it has become a kind of meta-discovery in itself, a recognition that the universe is reliably more complicated than the simplified pictures we build from incomplete data. The reaction within the scientific community to this pattern has been mixed. Some researchers have embraced the implications, arguing that the New Horizons findings along with similar surprises from other recent missions, point to the need for a more humble approach to theorizing about regions of the universe we have not yet visited. Others have resisted, suggesting that the surprises are individually accommodatable and do not warrant any fundamental reassessment of how we approach the science. The debate is not particularly visible from outside the field. It plays out in conference panels, in review articles, in the framing of grant proposals, and in the choice of which questions get pursued by which teams. The institutional structure of planetary science, with its emphasis on consensus building and incremental progress, tends to discourage dramatic public statements about how much we got wrong. The progress happens, but it happens quietly. The other reaction, less common but worth noting, is one of frustration. A handful of researchers, mostly junior scientists or those working at the margins of the field, have expressed openly the view that the official communications around the mission have undersold the significance of the findings. The story being told to the public, in their view, is too tidy. It emphasizes the confirmed and conventional results, and it minimizes the puzzles. It treats the unknowns as future work rather than as live questions that bear on how we understand the solar system today. This view is not the mainstream view within planetary science, but it exists, and it is worth taking seriously because the people expressing it are the ones who have spent the most time working with the data. The question of what these discoveries mean for humanity, beyond their narrow scientific interest, is one that the official communications around the mission have largely avoided. The press materials describe the findings in technical terms, emphasize the engineering accomplishments of the spacecraft, and celebrate the scientific milestones without dwelling on what any of it actually means for the people watching from Earth. This is, in some ways, an institutionally cautious choice. Scientists generally prefer to let the data speak for itself and to let the broader interpretation emerge slowly through the natural process of academic discussion. But the consequence is that the public narrative around New Horizons has become curiously thin. The mission was a triumph. The flybys were successful. The pictures were beautiful. And then, in the official telling, the story essentially ends, as if the spacecraft had completed its assigned tasks, and the only remaining question was how long it would continue operating before its power supply ran too low to send useful data. The actual situation is more interesting. The spacecraft is still flying. The instruments are still measuring. And the findings are still arriving, in slow trickles, in the technical literature, where they continue to suggest that the outer solar system is a more complex and more populated environment than the standard picture acknowledges. The question of what this means for humanity depends on what kind of meaning you are looking for. If you are looking for direct practical consequences, the answer is that there are not many. The Kuiper Belt does not affect daily life on Earth. The dust grains New Horizons is encountering are too far away to do anything to us. The structure of the local interstellar cloud is not something that influences weather or agriculture or economics. If meaning means immediate utility, the New Horizons findings have very little of it. But if meaning includes the slower kind of consequence that comes from changing how we understand our place in the universe, then the findings matter more. There is something significant about the realization that the solar system we inhabit is not the tidy structure that the textbooks describe, that there are populations of objects in regions thought to be empty, that there are organic compounds whose identities we cannot determine, that there are particle distributions that hint at gravitational influences from bodies we have not detected. These findings do not change anything we will do tomorrow, but they do change the picture we carry of what kind of place we live in. They suggest that the solar system, far from being a fully mapped territory, is still substantially unknown, even in regions that are technically within our reach. There is also a practical implication, more concrete than the philosophical one, that bears on how we plan future missions. If the outer solar system contains more material than the standard models predicted, then any spacecraft we send out there will encounter more dust, more debris, more potential impactors than mission planners had assumed. The hazard environment is not as benign as the original calculations suggested. This matters for designing spacecraft shielding, for choosing trajectories, for for estimating the operational lifetime of probes that have to survive long journeys through the outer reaches. The Voyagers, Pioneer 10 and 11, and New Horizons itself have all so far survived their passages through the outer solar system, but the dust counter results suggest they have done so in part by luck. A future mission, traveling on a different trajectory, might encounter a denser dust environment and suffer damage that the current generation of probes managed to avoid. There is also the question of life. The discovery of organic compounds on Arrokoth, including compounds whose identities we cannot fully determine, raises questions that the official communications have not dwelt on, but that are worth examining. The standard picture of how life arose on Earth includes the delivery of organic material from the outer solar system during the early bombardment phases. Comets and asteroids carried complex molecules to the inner planets, providing some fraction of the chemical building blocks from which terrestrial biology eventually emerged. If the outer solar system contains a richer and more diverse inventory of organic compounds than the standard models predict, then the material delivered to early Earth was also richer and more diverse than the standard picture allows. The chemistry available for the origin of life was, in this view, more complex and more interesting than has been generally assumed. This does not prove anything about the origin of life. It does not constitute evidence that life came from somewhere else, or that the early Earth had unusual chemical resources, or that biology elsewhere in the universe is likely to follow similar patterns. The connections between solar system chemistry and the origin of life are speculative and depend on a number of intermediate steps that are not well understood. But the connections are there. The findings from Arrokoth, taken together with similar findings from other outer solar system missions, suggest that the chemical environment in which biology emerged on Earth was shaped by inputs from a region of space whose chemical inventory we are still in the process of cataloging. If that inventory turns out to be more complex than the textbooks describe, then the picture of how biology got started on this planet may need some adjustment as well. The question of life elsewhere in the universe is also touched by the findings, though more indirectly. If the outer solar system contains structures and objects and processes that the standard models did not predict, then the planetary systems around other stars probably contain similar surprises that our remote observations cannot detect. The exoplanet community has been engaged for several decades in an ambitious project of cataloging the planets around other stars, characterizing their orbits and masses, and sometimes their atmospheric compositions. The cataloging has been wildly successful, with more than 5,000 confirmed exoplanets and many more candidates. But the catalogs are necessarily based on remote observations, and remote observations have limits. If the New Horizons findings teach us anything about how planetary systems actually work, it is that the population of objects and structures in any system is probably more diverse and more abundant than what we can detect from a distance. This has implications for the search for life beyond Earth. The conventional approach to that search has focused on identifying potentially habitable planets, worlds in the so-called Goldilocks zone where liquid water could exist on the surface. The assumption underlying this approach is that habitable worlds are relatively rare, and that the inventory of such worlds in our galaxy can be estimated from the inventory of detected exoplanets. But if exoplanet catalogs are systematically incomplete, missing populations of objects that our current methods cannot detect, then the inventory of potentially habitable worlds may be larger than the standard estimates suggest. The galaxy may contain more environments suitable for life than we have been counting, hidden in regions that our remote observations cannot probe with sufficient detail. This is not the kind of thing that gets headlines, because it is too speculative, too indirect, and too dependent on chains of inference that any individual specialist can challenge. But it is the kind of thing that, slowly, over time, changes the framing of how scientists think about the broader questions of cosmology and astrobiology. The New Horizons findings, taken together with similar findings from other recent missions, are nudging the field toward a recognition that the universe is more populated and more complex than the simplified pictures we have built from incomplete data. The implications of that recognition for how we think about our place in the cosmos and the likelihood of finding life elsewhere are still working their way through the field. They will continue to do so for many years. The questions that remain unanswered about the New Horizons findings are in many ways more interesting than the questions that have been settled. The mission has produced a long list of partial answers, of tentative interpretations, of measurements that suggest something without quite establishing what. The list of open questions is correspondingly long, and the work of addressing those questions will occupy planetary scientists, heliophysicists, and astronomers for years to come. Some of the questions can probably be answered with existing data, through more careful analysis of the measurements already in hand. Others will require new observations, either from New Horizons itself, as it continues to fly outward, or from new missions that have not yet been built or funded. The most pressing open question is the nature of the organic compounds detected on Arrokoth that current laboratory data cannot identify. The infrared spectra returned by the Ralph instrument contain absorption features that do not correspond cleanly to any single known compound. The published interpretation is that these features represent some combination of complex organic molecules, but the specific combination cannot be determined from the available data. Resolving this question will require laboratory work, specifically the production and analysis of candidate molecules under conditions that approximate the surface of Arrokoth, followed by careful comparison of the laboratory spectra to the New Horizons data. This work is in progress at several institutions, and it is expected to take years. The compounds in question may turn out to be variants of molecules that are already known, with their spectra simply not having been measured in the relevant conditions. Or they may turn out to be genuinely novel compounds that no terrestrial laboratory has previously synthesized. A related open question is whether the methanol detected on Arrokoth's surface really is as anomalous as the initial analysis suggested, or whether there is a process that can sustain methanol in the Kuiper Belt environment that the standard models did not include. The radiation environment in the outer solar system is harsh, with cosmic rays and solar ultraviolet light continuously bombarding surfaces and breaking down complex molecules. Methanol should not survive for 4.5 billion years under such conditions, and yet it is there, in quantities significant enough to dominate the infrared spectrum at certain wavelengths. Either the methanol is being replenished by some process we have not identified, or it is being protected by some mechanism we have not understood, or our models of methanol photochemistry under these conditions are wrong in some way. Each of these possibilities has implications. If methanol is being produced on Arrokoth's surface today, then there are chemical processes operating in the outer solar system that we have not adequately characterized. If it is being protected, then the surfaces of small Kuiper Belt objects may be structured in ways that shield them from radiation more effectively than the standard models assume. If our models are wrong, then a substantial body of laboratory and theoretical work needs to be redone. The dust counter results raise their own set of open questions. The measurements suggest that the Kuiper Belt extends much farther than the standard models predict, but they do not directly identify the bodies producing the dust at large distances. Those bodies, if they exist, are too faint to be detected by current optical surveys. Finding them will require either much more sensitive optical instruments than we currently have, or surveys at infrared wavelengths where small icy bodies emit more strongly relative to the background, or completely different observational strategies that nobody has yet developed. The Vera Rubin Observatory in Chile, which began its main survey operations in 2025, is expected to detect substantial numbers of new outer solar system objects over its 10-year survey period, but even Rubin will not be able to see the smallest and most distant bodies. The full mapping of the outer Kuiper Belt may require dedicated missions, including infrared survey telescopes positioned far from the Sun where the zodiacal light does not interfere. The pickup ion measurements from PEPSSI also leave significant questions unresolved. The excess energetic particles could be the signature of a denser pocket of interstellar gas that the heliosphere is currently interacting with, or they could reflect imperfectly understood physics in the outer heliosphere, or they could indicate the gravitational influence of an undetected massive body. Distinguishing between these possibilities will require additional measurements over longer baselines, ideally from multiple spacecraft positioned at different points in the outer solar system. Currently, only New Horizons, Voyager 1 and Voyager 2 are in the outer heliosphere, and the Voyagers carry older instruments with limited capability to make the relevant measurements. The Interstellar Mapping and Acceleration Probe, called IMAP, which launched in 2025, is providing some of the needed measurements from a closer position, but it cannot replicate the deep outer solar system perspective that New Horizons offers. The cosmic optical background excess detected from New Horizons remains, in some ways, the most consequential open question of all. If the excess is real and is not entirely explained by hidden populations of faint galaxies, then the implications touch on some of the deepest questions in astrophysics. There could be a previously unrecognized component of cosmic background light, perhaps associated with decaying dark matter or with some other process we have not yet identified. There could be a population of intergalactic stars, ejected from their host galaxies during galactic mergers, that contributes more light than the standard models include. There could be diffuse emission from the intergalactic medium at levels higher than expected, perhaps related to the ionization history of the universe in ways that are not fully understood. Each of these possibilities has consequences that extend far beyond planetary science, touching on cosmology, dark matter physics, and the history of structure formation in the universe. Resolving the cosmic optical background question will require additional measurements from outside the inner solar system, ideally with instruments specifically designed for the task. New Horizons will continue to provide useful data as long as it remains operational, but the spacecraft is aging, and its power supply continues to decline. Within the next decade or so, the spacecraft will no longer have enough electricity to operate its scientific instruments, and the mission will effectively end. After that, the unique perspective on the cosmic optical background that New Horizons currently provides will be lost, unless a follow-up mission is developed to replace it. Several concepts for such a mission have been proposed, but none have yet been funded or approved. The window for making these measurements may be narrower than people realize. Beyond these specific questions, there is the broader question of what other surprises the spacecraft may yet deliver. 5 years from now, 10 years from now, additional analysis of the data already collected may reveal patterns that nobody has yet noticed. The volume of data returned by New Horizons is substantial, and the team analyzing it is relatively small. Many of the measurements have not been examined in the depth they deserve, simply because the resources to do so have not been available. The history of space science is full of examples of discoveries that emerged years or decades after the original missions, when researchers returning to old data found features that the original analysts had overlooked. New Horizons is likely to continue producing discoveries of this kind for many years, long after the spacecraft itself has stopped transmitting. The data archive will be a resource for planetary scientists and heliophysicists well into the second half of this century. There is something worth pausing over in the larger pattern that the New Horizons story exemplifies, because it speaks to a question that goes beyond any single mission or any single set of findings. The question is what it means, as a species, to send a small machine billions of miles into the dark and to listen patiently, year after year, to the faint signals it sends back. The practical answer is that the machine gathers data, and the data informs our scientific understanding, and the scientific understanding eventually finds its way into textbooks and lectures and the slow accumulation of human knowledge. But there is another answer, less practical and more philosophical, that has to do with how we situate ourselves in the universe and what kind of project we understand ourselves to be engaged in when we do this work. For most of human history, the outer solar system did not exist as a category. People looked up at the night sky and saw stars and planets and the moon, and they built stories around what they saw, mythologies and cosmologies and theological frameworks that gave meaning to the lights overhead. But Pluto, when it was discovered in 1930, was not visible to the naked eye. It had been inferred from subtle perturbations in the orbits of the outer planets, then searched for with telescopes, then identified in photographic plates by a young astronomer named Clyde Tombaugh, who was doing the kind of patient, methodical work that gets discoveries done but rarely makes anyone famous. Tombaugh's discovery was the first time humans had identified a world that nobody had ever seen, that nobody had ever imagined in any specific way, that existed in a region of the solar system that had previously been a blank space in the maps. And then, 85 years later, a spacecraft built by people who in many cases had not yet been born when Pluto was discovered arrived at that world and sent back pictures of it. The pictures showed a place that was real, geologically active, complicated, with mountains and ice plains, and a thin atmosphere, and a sky that, if you had been standing on its surface, would have been a dark blue stretching toward the horizon. The world that had been a point of light, then a fuzzy blob in the best telescopes, then a slightly less fuzzy blob in the Hubble images, became a world with features and characteristics and a specific physical identity. The transformation took 85 years and required the work of thousands of people across multiple generations. And at the end of it, a place that had been essentially unknown became a place that we knew. This is what humans have been doing in various forms for as long as we have existed as a species. We extend our reach. We find out what is beyond the next ridge, on the other side of the ocean, on the Moon, on Mars, in the asteroid belt, at the rings of Saturn, at the edge of the heliosphere, in the Kuiper Belt beyond Neptune. Each step in this extension requires patience, often more patience than any single human lifetime allows. The New Horizons mission was conceived in the 1980s, approved in the early 2000s, launched in 2006, and continues to operate in 2026. The scientists who designed the instruments were not the same people who flew the spacecraft past Pluto, who were not the same people analyzing the data from Arrokoth, who are not the same people who will be analyzing the data from the spacecraft's final years of operation. The mission belongs to no single person and no single generation. It is a project that humans have been working on collectively, with contributions from people who never met each other and who in many cases never will. This collective and intergenerational character of space science is one of the things that makes it difficult to communicate to general audiences. The narratives we naturally build around scientific discovery tend to emphasize individual achievements, single moments of insight, dramatic confrontations between competing theories. The reality of how missions like New Horizons actually unfold is much less dramatic and much more diffuse. There is no Galileo at the telescope, no Einstein at the blackboard, no Watson and Crick at the lab bench. There are instead hundreds of people working in shifts on different aspects of an enormous project over the course of decades, with the achievements emerging not from any single act of brilliance, but from the accumulated effect of countless small contributions, each one essential, none of them individually decisive. The findings we have walked through tonight are products of this collective process. The Arrokoth observations were collected by a spacecraft built by hundreds of engineers, operated by a team of mission specialists, and analyzed by a community of planetary scientists, with the work distributed across institutions and countries and stretching over years. The cosmic optical background measurement involved a small group of researchers analyzing data from an instrument that nobody had originally planned to use for this purpose, building on techniques developed by previous generations of astronomers and publishing their results in journals that have existed for more than a century. The dust counter results came from a student-built instrument whose original purpose was as much educational as scientific, but whose data has turned out to constrain some of the most important questions in outer solar system astronomy. None of this is the way human knowledge advances in the popular imagination. There are no lone geniuses, no eureka moments, no single individuals whose names will be remembered in the way that Galileo and Newton are remembered. There is instead a vast collaborative enterprise, distributed across time and space and institutions, in which any given participant contributes a small piece to a larger picture that no one of them will ever see complete. The picture itself is built slowly, with frequent revisions, and is never finished. Every new measurement reveals features that previous measurements had missed. Every new mission opens up questions that the previous missions had not been able to address. The work is, in this sense, permanently incomplete, which is both its frustration and its grandeur. When you think about what New Horizons has actually done, in the largest possible terms, you arrive at something like the following. A small piano-sized machine, built by humans on Earth, launched in 2006, has spent 20 years traveling outward through the solar system, has passed by Pluto and Arrokoth, has measured the dust and particles and ultraviolet light in regions of space that no previous machine had reached, and has continued sending back data that, slowly and quietly, has been changing our picture of what the outer solar system is like. The machine itself, 4 billion miles away, knows nothing about any of this. It executes its programmed instructions, sends its data home, and waits for the next instructions, indifferent to the human meaning that gets built around its measurements. The meaning is something we build on Earth from the signals that arrive. The machine is just a machine, but the meaning is real. The picture is changing. The outer solar system, in the maps we will draw a generation from now, will look different from the outer solar system in the maps we have today. The textbooks of 2040 will not say what the textbooks of 2010 said. And somewhere in the chain of reasons that led to those revisions, there will be the data sent home by this one small spacecraft in the years between Pluto and the eventual exhaustion of its power supply. That is a kind of legacy that does not depend on any individual being remembered. It is the legacy of the collective work itself. So what should we make of all this, finally, at the end of a long walk through the discoveries that a single small spacecraft has delivered from the dark beyond Pluto? The honest answer is that we should hold the story carefully, with appropriate respect for both what has been found and what remains unknown. The findings are real. The data is public. The implications, while not as dramatic as the framing of this video has perhaps suggested, are genuinely significant for how we understand the outer solar system and our place within it. But the framing matters too. The idea that scientists are hiding things from us in any active or coordinated sense is not quite right. What is happening instead is something more mundane and in some ways more interesting. Scientific institutions, when they communicate with the public, tend to emphasize the findings they can interpret confidently and to soft-pedal the findings that remain ambiguous. This is not a conspiracy. It is a cultural pattern within the scientific community, one that has both reasonable justifications and real consequences for what the public learns about ongoing research. The reasonable justification is that overclaiming is genuinely damaging. When scientists communicate uncertain results as if they were established facts, the eventual correction can damage public trust in ways that are difficult to repair. The history of science is full of examples where early, exciting claims turned out to be wrong, and the public memory of those reversals lingers far longer than the memory of the eventually correct picture. Institutional caution, in this context, is a way of protecting the integrity of scientific communication over the long term. The cost of being too cautious is that the public gets a flatter, less interesting version of the actual scientific story. The cost of being too aggressive is that the public stops believing anything scientists say. Most institutions, faced with this trade-off, lean toward caution. But there is a real cost to that caution, and the New Horizons story illustrates it well. The actual scientific situation, with all its puzzles and tentative interpretations and unresolved questions, is more interesting than the official narrative that emphasizes confirmed findings and engineering accomplishments. The Arrokoth chemistry, the dust countermeasurements, the cosmic optical background excess, the ultraviolet structure of the local interstellar medium, the pickup ion anomalies, all of these findings, taken together, suggest that the outer solar system is a more complex and more populated environment than the textbooks describe. The pieces of evidence do not yet add up to a single coherent revised picture, but they suggest that one will eventually emerge, and that the emerging picture will be richer and stranger than the one we have today. This is the story that gets lost when the communication emphasizes the tidy results and downplays the loose ends. There is also, in fairness, a real possibility that the loose ends will turn out to be less significant than they currently appear. Some of the New Horizons findings may eventually be reconciled with the standard picture through improvements in the models or through better calibration of the instruments. The cosmic optical background excess may turn out to be largely explained by hidden populations of faint galaxies once the next generation of telescopes catalogues them. The dust counter measurements may turn out to reflect a less dramatic extension of the Kuiper Belt than the initial interpretations suggested. The pickup ion anomalies may be absorbed into refined models of solar wind physics that do not require any exotic new components. Scientific puzzles, when examined carefully over time, often resolve into less dramatic answers than the initial framings imply. The history of astronomy is full of mysteries that turned out to be measurement errors, of anomalies that became conventional once the instruments were better understood, of revolutions that became modest refinements once the dust settled. Some of what we have walked through tonight may follow that trajectory, but some of it may not. The pattern of consistent surprise from outer solar system missions, the repeated finding that the actual environment is more complex than the predicted environment, suggests that at least some of the New Horizons puzzles will hold up under further investigation. The exact shape of the eventual revised picture is impossible to predict from where we sit now, but it will probably include more objects in more places, more chemistry of more kinds, more structure in the local interstellar medium, and possibly the presence of additional bodies in the outer solar system that current optical surveys cannot detect. The textbooks of the future will look different from the textbooks of today. The mission that helped make them different was a small piano-sized spacecraft, launched in 2006, still operating in the cold dark, still sending its faint signals home. And then there is the question of what comes next. New Horizons will not operate forever. The plutonium in its power supply continues to decay, and the available electricity continues to decline. Within the next decade, possibly somewhat longer if the team finds ways to operate the spacecraft more efficiently than current plans allow, the probe will lose the ability to power its instruments and will fall silent. After that, it will continue to drift outward, a quiet machine in an empty region of space, eventually crossing the heliopause and entering the interstellar medium, eventually traveling on a trajectory that will carry it, over millions of years, into the wider galaxy. By the time it reaches anywhere recognizable, the civilization that built it will have changed beyond imagining or will have ended. The spacecraft will be a small artifact of an early phase of human exploration, drifting through space, no longer in any meaningful sense a participant in the project that built it. That is the long term. The short term is that we have perhaps another 5 or 10 years to extract as much science as possible from the instruments still operating. There are measurements that have not yet been made because the time and resources to make them have not been allocated. There are analyses of existing data that have not yet been done because the team is small and the data is voluminous. There are connections between findings that have not yet been drawn because the relevant specialists work in different fields and do not always talk to each other. The work that remains is substantial. Whether it gets done well, or partially, or not at all, depends on decisions about funding and personnel and institutional priorities that are being made now and will continue to be made over the next several years. These decisions will determine how much we ultimately learn from this mission, and they will be made largely outside public view, in committee rooms and grant review panels and budget meetings that no headlines will ever cover. If you find this story compelling, if you want to see this kind of patient, careful, unglamorous science continue to deliver findings from the edges of what humanity can reach, the thing that matters most is sustained public interest in space exploration as a long-term enterprise. The missions that are operating now were funded by decisions made decades ago. The missions that will be operating in 2050 will be funded by decisions being made today. Whether those decisions support ambitious exploration of the outer solar system or retreat to less ambitious goals closer to home depends in part on whether the public continues to find this work worthwhile. Thank you for spending this time with me, walking through the discoveries that one small spacecraft has delivered from the cold dark beyond Pluto. If this kind of careful storytelling about space and science is something you value, take a moment to like this video, subscribe to the channel, and share it with someone else who might appreciate it. Leave a comment telling me where in the world you are watching from, because the audience for this kind of work is global, and it is genuinely interesting to see where the curiosity lives. The universe is older and stranger and more populated than the textbooks describe, and the work of mapping it is far from finished. There is more to come from this mission and from the ones that will follow it. Keep looking up and keep wondering what is out there waiting to be found.